Today we are going to talk about the HRRRCast, or data-driven emulator for regional weather forecasting at convection allowing scales. Our main developer is Daniel Abdi, and we also have a lot of collaborators, both from GSL, which is Paul Madden, Vanderlei, Vargas, from PSL, Tim Smith and Sergey Frolov, and from National Severe Storm Laboratory, Monte, Flora, and Potvin. Oh, my slides are not moving. Oh boy. Sorry. So it seems like slideshow. Oh, okay. I don't know what I did.
I see it moving now. Yeah.
Okay. Yeah, and I'm not sure what I did where I clicked, but so I'll try not to move the mouse. Okay, well, first thing I want to share that just recently the GSL went through the kind of exercise of revisiting our strategic plan in preparations for our upcoming lab review that's next year. And obviously, usually you do these strategic plans for 5 to 10 years, and AI was not part of our last strategic plan. And obviously, things are moving fast. So just within a year, this became one of the highest priorities of the lab, one of the important or highly important activities within a lab. So just this year, we went through the process of reformatting or revisiting our strategic plan and had a special session on AI for NWP. And by going through that exercise, we identified two major priorities, one being pursue development of pure AI data-driven model at convection allowing scales, and another one, equally important, develop verification and validation system and techniques to evaluate AI models for a variety of applications. Well, being at Global Systems Laboratory that originally was the developer of the high-resolution rapid refresh model, it made sense now in this new era, new technology, and examining use of AI for NWP to focus on the HRRR scales and HRRR both spatial and temporal scales. So let's see if the moving slides work. It does. So HRRR being over the high resolution, meaning 3 kilometer grid spacing covering the conus area. Again, it made sense for us from GSL to kind of focus first on HRRR. And at the beginning, we tried to focus on the full conus, and it became clear at the time with the resources, computational resources that we had available, that we will not be able to neither train nor execute model at that resolution and over the full conus. So in order to first kind of exercise and learn about these AI-based models and algorithms, we started with the smaller domains, and not being in situation to have a fully funded project, we start to utilize resources from other funded projects, one being Water in the West, focusing on the western part of the United States, and some of the projects focusing on convection, convective weather, and obviously focusing on the Central Plains. So we started with the two small domains with our development, one, as you can see, with the red box over the western domain, and one in the Central Plains with the green box. Our original development started with obviously focusing on a smaller domain, as I just talked, 3 kilometer with the 3 kilometer grid spacing, and using HRRR data that we have available for training. And the available consistent HRRR data that we have available is 3 years of data. And our original development started with evaluating two different algorithms, one being based on GraphCast and one being based on in-house developed ResNet model. The GraphCast, which we from now on, I will refer to that as GraphHRRR, and the other one I will refer as the ResHRRR. The GraphCast obviously based on a model developed by Google DeepMind, which was for the global application. So in order for us to use this for regional applications and a much higher resolution, it required a lot of modifications. And this is the part where we really have to give credit to our NSSL colleagues, because we worked with them in order to make the necessary modification to GraphCast to accommodate regional application. Regarding the ResNet-based model, which we called ResHer. It was in-house developed. It also started as a global application, but then it was much easier adopted for regional applications because it was well-known code developed by Daniel. Also, we decided that we will use two different approaches, deterministic and probabilistic. And with deterministic, we usually talk about one single instance of the model, and probabilistic meaning that we have an option to run ensemble and create probabilistic approach. But more precisely here by probabilistic, what Daniel, who made these slides, meant is that we were able to attach, to develop, or actually to include the denoising diffusion implicit model, or DDIM, within ResHer, which would allow us to create multiple instances or multiple ensemble members, therefore be able to, in the future, work on a probabilistic forecast. I'll say now that this hasn't been done for GraphHer yet, because again, that's another reason that in a recent couple of months, the major development was focused on ResHer and in-house model, because simply at some point it became really clear that GraphCast is too complicated and it's not code that we developed. So it was just increasingly harder and harder to add new features and add new developments. So the most recent developments and most recent results are really just achieved by ResHer, and those are most of the results we will talk about later in the presentation. So models were trained for 1 hour, 3 hour, and 6 hour lead times, and then rolled out up to 18 hours. That was the goal, to get longer lead times. For both versions of the models, we had 6 atmospheric variables, 12 pressure levels, and 2 surface variables, reflectivity, composite reflectivity, and 2 meter temperature, where composite reflectivity will be used as a proxy for precipitation. Okay, this is where I wish Daniel is here. Daniel, are you here?
Yes, yeah. I'm here. Yeah.
Okay, well, please take it from here.
Thank you, Isidora, for taking care of the first few pages. Yeah, so this is the architecture of the ResHer, which we call now HRRRCast. In the green top row, you see the inputs that we are taking in. We have about 74 channels from her. Those are like 6 atmospheric pressure, 6 atmospheric variables, and 2 surface levels. And for the diffusion model, we noise these her inputs with a Gaussian noise, and that adds an additional 74 channels. And the other important input is the GFS input. So you need to take into synoptic information, because this is a limited area model. Unlike the global area model, you have to use the GFS input as a conditioning as well. We have additional variables like orography and landmass, which are static, that doesn't change with time. And finally, we have also lead time and the diffusion step as an input, and these are directly fed into each processor block, each encoder block, and this helps the network to condition its outputs based on the lead time and based on also the diffusion step. And we have found that this to be useful particularly for the diffusion model. Next slide, please. This is the architecture of GraphHer. We were not, that successful with the result, but we expect that the graph-based method will be the final version of HRRRCast. So we originally started from the NSSL effort, which is called WOFScast, and this modified the GraphCast architecture to work with the limited area domain. And the main changes are, like, instead of the spherical domain and the icosahedral mesh, it uses the HRRR grid and a rectangular or a triangular grid shown in these figures. And we've made additional modifications to make it work with the HRRR grid, which is an LHC projection grid, not a typical latitude longitude grid. And after those modifications, we are able to get the GraphHer also working with the limited area domain. Next slide. So this is the primer on generative AI. I'm sure you're all familiar with it. So the main idea behind diffusion models is that you noise the input weather state with a Gaussian noise. So that's progressively done with 200 steps in our case, but typically it's like 1,000 steps. You noise it with a Gaussian noise, and then you train a neural network to hopefully learn the denoising process, and gives you, a pure image without any noise. And as you can guess, so if you are doing like 50 steps for during the inference, that will be like 50 times more expensive compared to a typical, deterministic model. So there is some cost associated with generative AI, but you could use it to produce ensemble members for your simulation. So that's the advantage with the diffusion model. Next slide. So what are our options to add, to add different perturbations to the initial condition, maybe the initial conditions, or also like during each denoising step, you have the option of adding some noise, which is analogous to like in a physics-based weather models, that would be equivalent to perturbing the physics. And the other option that we have is you could also, change the initial noise, and that's actually what we used for our work. Like we just changed the initial noise when we were happy with the result. There was enough spread between the different ensemble members, and when we compare like the spread error ratio, it was more or less the same as the standard Herr model. Next slide. So here I'm comparing the diffusion versus deterministic. On the left column is the Herr analysis, which is our target. Second column is the Herr forecast. Third column is our one member HRRRCast prediction, and the final one is the deterministic. So clearly, the deterministic shows a lot of blurriness. It's smooth compared to the diffusion model. So that's the advantage. But if you compare like root mean square errors between the the diffusion model and deterministic model, the deterministic model typically has a lower root mean square error. So that's the problem with deterministic forecast. It captures, on average, like what it should be, but like if you want sharpness in your forecast, then it's not gonna work for us. But overall, deterministic model is also competitive, and I'll show the results later, where it is the best performing model in terms of root mean square errors. Comparing Herr analysis versus Herr forecast, we are kind of surprised to see that Herr forecast typically tends to over predict, or like if there is a storm, it over predicts its intensity, and it's sort of shown in this figure as well, where you have a lot of red dots compared to the Herr analysis. Next slide. Here I'm comparing a 10-member ensemble, our 10-member ensemble, versus Herr analysis versus deterministic racer and deterministic grapher. So you can see that grapher is particularly, it lacks a lot of features, like it doesn't accept GFS input, it doesn't fine-tune its results on longer lead times, and because of that, it's currently not performing as well as the other models. But if you compare the 10-member HRRRCast prediction versus the Herr analysis, they are more or less close to one another. And I'm not showing the Herr forecast here, but Herr forecast over predicts, while our model tends to align more or less with the analysis. Next slide. And comparing the power spectra of different models, here the green line is showing the deterministic racer. So you can see that it's dissipating a lot of small scale features. And the red line is the grapher. It's better than the deterministic racer, but still, dissipates a lot of small scale features. But looking at the diffusion model, which is the orange line, it is more or less on top of the Herr analysis, which tells us that it is capturing the fine scale structures, and it's doing pretty well. And I'm not sure I'm showing here the Herr forecast, but the Herr forecast is also not, not on top of the her analysis, which tells us that there is some disparity between the observations and what her is predicting. So while our HRRRCast more or less try to, is on top of her analysis, her forecast is not. So that was kind of a surprise for us. And the story is the same at 6-hour lead time. Just the one on the left is 1 hour lead time. It's more or less the same, except for the fact that, Grapher is more dissipative now, like at longer lead times. Next slide. For the other variables other than composite reflectivity, all the models more or less have the same power spectra. So it means it tells us that the advantage of diffusion models for our case is particularly for precipitation related variables like composite reflectivity. For the other variables, we could have as well used the deterministic model. Next slide. Here is our main result, the fraction scale score on composite reflectivity. On the top row, I'm showing an 18 hours forecast on a 10 days data set. And on the second row, I'm showing a 4 months, that's the entire evaluation data set, but this is done at 6-hourly intervals. Due to the cost of the diffusion model, we couldn't do like an hourly interval. So our main result is that at 20 dBz, it outperforms the HER model. Beyond like 3 ensemble members, it outperforms the HER model at 20 dBz, and it's sort of competitive at 30 dBz, but it's not that good at 40 dBz. So one thing I'd like to caution is that at 40 dBz, HER is not performing well because typically like the fraction skill score has to be above 0.4 to say that a model has some skill. But here you can see that it's 0.1 or something like that. So that's the main result. Like at 20 dBz, our model seems to be outperforming her. Next slide. Comparing the other standard metrics. So here in the middle, we're showing the frequency bias, where the blue line is her and the red line is our model. So the ideal frequency bias is 1. So you can see that her is over forecasting storms. The blue line is her. The red line, ours is a little bit more or less closer to 1.2. It's under forecasting, but I think I can say from this figure that it's closer to the truth than her is. And on the left, I'm showing critical success index, and the story is the same. Like the 10-member ensemble member is better than her, which is the blue line. And with regard to the performance diagram, here also like the under forecasting, over forecasting nature is shown, where the diagonal line, like if it is above the diagonal line, it means it's over forecasting. That's her, the blue dots. The red dots, that's our model. And the closer you are to the top right corner here, the better. So our 10-member ensemble is closer to the top right corner. So again, these metrics are showing that HRRRCast could be better. Next slide. This is the root mean square error plot I mentioned earlier. So the purple line here, that's the deterministic forecast. So that's the best one. So it's kind of surprising, but not like if you think a little bit more into it. So the deterministic has the best one, followed by the 10-member ensemble. That's the diffusion model. And her is the blue line, particularly like on vertical velocity, her is not doing that well. We were not sure why that is, but also our results, like I'm not sure I'm showing it in these slides, but our other results show that her kind of over predicts vertical velocity as well. So our model does pretty well on that as well. Next slide. Next slide I'll pass this slide. Next slide. Here it's showing like 1 out to 10 ensemble members. Like when you first look at it, you don't see a lot of spread between the ensemble members. So we calculated spread error ratio. Next slide. Here I'm showing like spread error ratio for different variables, and the average is about like 0.6, which is more or less the same also for her. So even though it didn't look initially like there was a lot of spread between the members, turned out that there is, and that would be obvious, like with object-based verification that Vanderlei will talk about. Next slide. Yeah, next slide. I think I'll stop here and hand it to Vanderlei to save some time.
There's just one question for you real quick, Daniel, in the chat from Ben Cash. What is the FILM block in the HRRRCast architecture? Just maybe one quick question. Thanks, Daniel.
Okay, so the film block is it's used for time conditioning. So typically, like, we're training a single model to predict 3 different lead times. So if you just feed the lead time information at the beginning of the network and forget about it, then it might not be, condition its output based on the time conditioning because it will forget about it. So the film block accepts those time informations, passes them through like a dense neural network, and then feeds that information to each encoder block so that the output will be conditioned on those time informations which are critical. Like when you're training like a single model to predict multiple lead times or multiple diffusion steps. So that's why the film block is important to have.
Thank you.
Thank you, guys.
Thanks, Daniel. So I don't have a whole lot to talk about this topic here. We're still working on generating the results, but I think it's important to show a different perspective, really, in terms of verification, to make sure that we are on the right path here. So I'll talk a little bit about object-based verification and how we approach this type of verification. One of the challenges here is to deal with this large data set. For this specific study case, for example, we have more than 26,000 lead times to process. We have one initialization every hour from May 1st, 24 to May 10th, 24. Then for each forecast, we have 12 lead times, and we have a total of 10 members. The first thing we have to do, because Math still doesn't support the native format used by the AI model, is to convert this 26,000 lead times into 26,000 CF compliant netCDF files. Once we had that, we are able to run the GNSProd tool, which is a tool provided by the MathPlus package. And the goal here is to create probability fields based on the ensemble members distribution. I don't think if Daniel got to this point, but we are looking to PMM as well to analyze the ensemble members, but we are also looking at using these probability fields to compare against observations. Basically, what we do here is to collapse the 10 members into one probability field. So the 26,000 files turn into about 2,600 files. Next, please. The next step was then to generate the same probability fields for the HRRR forecast and the HRRR analysis. And here you can see an example of this probability distribution for HRRR forecast, and the HRRR analysis, which we consider the truth, and we are comparing against it. Yeah, we recognize that this is not usual. It's not usual to compare an ensemble model directly to a deterministic one, but this is the way that we approach it for now. Next. So after pre-processing all that data, we are then able to run mode, which is also part of the MathPlus package. With mode, we can then calculate objects and compare those against the observations. There are several parameters when running mode, and we are still adjusting those, but basically mode takes into consideration attributes like centroid location, intensity distribution, area, orientation, and other parameters to calculate then the statistics associated with each forecast. Next. And here are some of the preliminary results that we have. We observed that HRRRCast has higher probability detection score, and at the same time, a lower false alarm rate for the threshold of 20 dBz. So we are just looking at the reflectivity for now here. For the frequency bias, the ideal value is around 1, and you can see that HRRRCast also shows a better performance there. As well as when we look at the CSI or at GSS. This confirms the same verification results that we observed in the grid-based verification that Daniel showed. Again, this is just a different perspective for verification, and we're still working on it, and hopefully we'll have more results soon. I think that's all I had. Thank you, everyone.
Yeah, thank you very much. Just monitoring the chat, I think we just have one question. As you mentioned, the deterministic forecast shows how shows high scores because metrics like RMSE favor smoother predictions. So which metrics could be considered more robust to this effect?
Yeah, so so on the root mean square error, the deterministic model does very well, but this project is mainly concerned with predicting precipitation. So we'd like to see it perform well on the fraction scale score as well. But in the figure, you can see that particularly like on 30 dBz and 40 dBz, the deterministic model has almost no skill at all. Like 40 dBz is 0. So yeah, we want it to perform very well on FSS. It's not doing that, but for the other variables, the deterministic model is competitive. Yeah.
Yeah, thank you very much. I think those were all the questions that I see in chat. Does anybody else have any questions? Yeah, James?
Yes. How often do you train the data for the HRRRCast?
Then you are muted.
I'm sorry, I didn't hear the question.
Can you hear me?
Yeah.
Oh, how often do you train the data for the HRRRCast?
Oh, right now we just trained the model once on a 3-year data set that goes from 2021 to 2024. But yeah, in the future we'll be training that model continuously with as new data comes.
Oh, so it's static training, so just kind of one time and then run the model.
Yes, so right now it's just trained once and we're evaluating, but in the future we'll be using 7 years of her data set, taking like additional 4 years that we can use, and also we'll be using up to 2025 data set.
Okay, thank you.
Yeah.
Okay, we maybe have time for one more question if anybody else has any. Okay, with that, Daniel, Isidora, Vanderlei, thank you very much for your time.